Hello, science students. I hope you are enjoying studying the electromagnetic spectrum and in particular your wave. So whether you have radio waves or gamma rays or anything in between, there seems to be one task that some of you struggled with a little bit that I'm going to help you with. All of you have been looking at the following task, and the one that we've been getting some questions about is this one. Explain and use the equation to calculate the frequency of your wave for a given wavelength. So let's take a look at this together. So first of all, you're asking yourself then, what does this mean? And if we see some things that we don't understand, what are we going to do? We are going to Google it. So it says here F equals C divided by some character you may have never seen. So put that into a search bar and let's see what we get. So I have, actually, let me go back. I've put this in a search bar and looked it up. And there's obviously tons of information that becomes available. So I have then clicked on one of these and just explored it a little bit further. And this particular site gives us some good information. First of all, you already know what frequency and lambda are, or wavelength are. Lambda stands for wavelength. And here in this point, it gives us the equation. So F equals C divided by lambda. And it says the formula for the frequency of light waves, any electromagnetic wave is a light wave, is F equals C divided by lambda, where C is the speed of light. Aha, so C is the speed of light. And when we click on that, we can see that the speed of light in empty space, oh, what has happened here? Let me go back. C is the speed of light, and we can see that the speed of light in empty space is a universal physical constant. This means it's the same everywhere in empty space and does not change with time. Physicists often use the letter C to denote the speed of light in empty space. It is exactly 299,792,458 meters per second. That's a lot. Okay, good information. So let's go back to what we were looking at. So we know that this equation gives us the relationship between frequency and the wavelength of an electromagnetic wave. We know that frequency is F is 1 divided by seconds, or 1 per second, or second to negative 1. What does that mean? Well, it means that, say I have a frequency of 10, that means that 10 waves are passing through a certain point per second. If I have a frequency of 1/10, then it takes 10 seconds for one wave to pass by in a certain point. My frequency is 100, then 100 waves pass by a certain point per second, and so on. Next, we have the wavelength. The wavelength is always given in meters or some form of that. And then we know speed of light. We also know the amount that is. That's 299,792,458 meters per second. That's a mouthful. I would like for us to use the scientific notation and just make it a little bit simpler. And we can just abbreviate it or round that to 3 times 10 to the 8th meters per second. Or in other words, 3 times 10 to the 8 meters per second is 300 million meters per second. That's really fast. Okay, back to our question. Explain and use the wave equation to calculate the frequency of your wave for a given wavelength. All right, so let's do that. You probably have something that you can write on. Rather than doing this in your slides, I think it's easier just to write it and take a picture of it. You can write it on a piece of paper, maybe a whiteboard, or maybe something special here. I'm going to use Snip and Sketch. I don't know whether you have that capability, but let's see here. So we always write our frequency, and then we are going to use C over lambda. Always write your equation first, then you substitute the numbers. So my C is the 3 times 10 to the 8th meters per second, all right, over lambda. So for lambda, you have a choice. You just need to choose a wavelength in the range for your particular type of wave. All right, so let's take a lambda, let's say a longer one. Let's say it's 100 meters. All right, 100 meters in scientific notation, we can say is 10 to the 2. All right, so 3, oh, I'm sorry, I need to put a unit here. That's meters. So 3 times 10 to the 8th divided by 10 to the 2 is 3 times 10 to the, well, let's take a look here. When we divide, we need to subtract. So 8 minus 2 gives us 6. In other words, 3 million. And then we can see this will be divided by that. So the meters will drop out and we have our 1 per second unit, or we can also write that as second to the minus 1, whichever you prefer. And that's our answer for that specific wavelength. All right, so we get 3 times 10 to the 6th. So in other words, 3 million waves, each of a length of 100 meters, are passing through a certain point. That's a lot, right? That's crazy much. All right, let's do another example. I hope this helps so far, but let's do another example. So again, I'm going to sketch. I'm going to start over again. So my F is C divided by lambda, and that is 3 times 10 to the 8 meters, per second. And now let's take something smaller. Let's say something in the nanometer range. All right. So let's say 6 nanometers. If you don't know what nanometers are, what should you do? You got it. You should look it up, right? But I'll help you a little bit here. Nanometers is a form of meters. It's a 10 to the 9th meter. So we have millimeters, 10 to the negative third. We have micrometers, 10 to the negative 6th, and then nanometers are 10 to the negative 9th. So it's basically a billionth of a meter. It's very small. So 6 times 10 to the negative 9, right? And this is just an example, right? You need to just choose your own wave length, meters. All right, so the nice thing by scientific notation, it makes our life really easy. 3 divided by 6 is 0.5. And then 10 to the 8th divided by 10 to the negative 9. So when you divide, you need to subtract. So 8 minus negative 9, that will become 8 plus 9. And that will give us 8 plus 9, that gives us 10 to the 17th. All right. Now, we don't like to have this decimal point here. So what we're going to do is we're going to change this into 5. All right. We can think of a half as 10 to the negative 1. All right. I'm sorry, it's 5 to the negative 1. So we need to subtract. So we have 10 to the 16th here. And that would be our answer. All right. And that again is second to the negative 1, right, per second. So 5 times 10 to the 16th per second. Holy moly, that is a huge number. I hope this helped. Good luck and enjoy your wave research.